All right, sorry about that. So concave downward. Okay, so concave upward looks like a happy face. It's like a cup or a bowl pointing up to the sky. And then concave downward is if we turn the bowl upside down, or it's like a sad face. Okay, so now that we have a basic definition, let's see how we can put a calculus twist to that. So let's draw two functions. We'll draw a concave up function and we'll draw a concave down function, and we'll relate it to the derivative. Okay, and so we know the derivative is the slope of the tangent. So let's look at all of the tangent lines for our f function. And then again, we can look at all of our tangent lines for our concave down function. Okay, so for these two cases, notice when it's concave up, and it could be on either side, I just drew an increasing, but same with decreasing, the function lies above the tangent. For concave up. And when we're concave down, the function lies below the tangent. And again, it doesn't matter which, if we're increasing or decreasing concave down, it's going to lie below. Okay. Okay, so how is that going to help us? What kind of calculations can we do with that? Well, let's draw a graph, and we'll draw a graph with concave up sections and concave down sections, concave up sections. All right, and first of all, did you notice how we went, let me get my highlighter. I'll do concave up, and then we switched to concave down or upside down bowl. Then at some point we switched and we started drawing concave up again, our right side up bowl. Okay, so we have these different periods of concavity. They kind of blend into the other. There's a definite point of change of concavities, and that point is called an inflection point. So let me get that definition out of the way before we go back talking to the derivatives. So the inflection point is where the concavity changes. Inflection points where the concavity changes. All right, and again, this is our concave up, concave upward, concave downward, and then our concave upward again. Okay, and let's relate it back to tangent lines. So when it's concave up, let's look at the tangent lines and the slopes. Okay, we'll do the same thing here. So we're drawing kind of tangent lines and thinking about the slopes. All right, and we go from a negative tangent, so negative slope, and it gets less and less negative till it's 0, and then it gets out slightly steep and it gets more and more steep. So what's happening is that the slope of these tangent lines is increasing. It's going from negative to positive. So I'm going to write that down. So slopes of tangents are increasing for concave upward. All right, let me switch colors to clarify. We'll go purple. Okay, and next for concave down, if we were to draw our tangents, it's positive at first, it gets less and less steep to 0, and then it's going more and more negative. We're going from positive to negative. So when it's concave down, the slopes of the tangents are decreasing. So when we're talking about when we're talking about slopes of tangents, that's f prime. So we're really saying that the derivative is increasing. The derivative is decreasing. Okay, so if we're saying something is increasing or decreasing, we're talking about the rate of change. So we're saying that the rate of change of the derivative is increasing. Well, the rate of change of the derivative, can you guess what it is? It's the double derivative. So the double derivative describes how the derivative or the slope of the tangent is changing. And if we're increasing, we know that means the double derivative is positive. That's going back to the first derivative rule. If something is decreasing, we know the rate of change is negative. All right, so again, if something is increasing, rate of change is positive. Something's decreasing, rate of change is negative. So we can talk about, when we talk about concavity, we're talking about the double derivative, okay? And that's going to take us to something called the concavity test. Okay, so if f double prime is greater than 0, the double derivative, for x in some interval I, then the graph of f, going all the way back to f from the double derivative, using that to give us information about f, of f is concave upward on that interval. Okay, and now if the double derivative is negative, we're concave down. I'll kind of abbreviate it here. Concave downward, okay. All right, and then we talked about those inflection points, and the inflection points are where the curvature changes. So let's write it out. A point P is let's start over. Let's be more specific. On a curve, a point P on a curve y equals f of x is called an inflection point if f, first of all, is continuous there, so no leaps or jumps or anything, and the concavity changes. And the concavity changes when f double prime has a sign change. All right, so that's another way of saying that f, the double derivative of f, has a sign change. Okay, so let's practice that. So let's go back to number 10. All right, if you remember, that's this function. And on this function, we have done a couple things. We have, I'll say recall. We know that it's increasing. The function f is increasing on these intervals. That's what we did at the beginning of this section. It's decreasing in between. We know there's a local max. We said at 1, so the local max, we would have to plug in 1. And if we did, we would get the ordered pair 1, 2. And then the local min, we said happens at 2, so we would have to plug it into the function. And if we did, we would get 1. So now we're going to graph let's go ahead and focus on the graph of this. And the last thing we need for the graph is the intervals of concavity and those inflection points. And intervals of concavity is the double derivative. Okay, so here we go. So to figure out the local mins and max, and if the function f is increasing or decreasing, we took the first derivative. That's what we did before. And now we're going to look at the intervals of concavity. So we have to go again. The double derivative, okay? So to figure out the sign changes, we need to find the zeros first. So set that double derivative equal to 0. Add 18, divide by 12. So we're looking at 3 halves. Or 1.5. Sometimes when we're graphing, it's easier just to figure out the decimal. Okay, so we're going to do the same thing again. To figure out the intervals of concavity, we're going to look for, we have where the inflection point could be. Remember, always label these little number lines so you don't get confused, because, you know, we're dealing with f, f prime, f double prime. So we have to see if we're positive or negative to the right and to the left, okay? So here we go, 12x minus 18. If we were to plug in a 2, right, 24 minus 18 is positive, all right? So there you go, if we plug in a 2. So we're positive to the right. And then to the left, we can plug in a 0. We get negative 18. And so we're negative to the left of 1.5. So this tells us our concavity. We're concave downward where it's negative. And then we're concave upward where it's positive. All right, and since the concavity changes at 1.5, 1.5 is our inflection point. Okay, 1.5 is the inflection point. So let's also have some space for that. So the inflection point is 1.5, and then we'd want to plug it in as well. So go back up to the original function, all the way up over there, right here, and we're going to plug in 1.5. And it ends up being 1.5. Okay. So now we're ready to graph, and we're going to graph all the things. We're going to show where it's increasing and decreasing. We're going to show local mins, local maxes, which we could only guess before, right? When we were dealing with these kinds of graphs in pre-calculus. We can only be like, oh, it kind of looks like this. But now we know exactly where the local min and local maxes are. We can demonstrate concavity. We can demonstrate the inflection points, all right? And I always like to throw in another point. If we throw in a 0, that will at least get us a y-intercept. And that happens at the point 3. F of 0 equals 3. So we can plug in, negative 3. All right, zeros are normally pretty easy to plug in. See, if we plug in 0, we get negative 3. All right, let's graph all of this. Okay. So I think we can go up 3 and down 3, and that will give us a pretty good palette to start with. Okay, I'll just go from the top up, or I'll start here. We know this is happening. That's a y-intercept. We have an inflection point at 1.5, 1.5. And I'll just say IP for inflection point so I don't get confused. Local min and max. So 1, 2 is the local max. And negative 1, 2. Wait. Oh, I'm sorry, I'm thinking of a different function. 1, 2 only, and then 2, 1 is the local min. Sorry about that. 2, 1 is the local min. Okay, so I'm just going to write local max, or I'm just going to write max, local min. Okay, and then the last thing we need is our areas of concavity. So our concave down to the left of 1.5. So here's our 1.5. So think of our function as having that shape. And then to the right, we're going to be concave up. So think of it as the cup. Okay? And we're going to connect all the dots, keeping that concavity in mind. All right, so concave down, here we go. All right, and then right there, our concavity is going to change. We're going to be more of a happy face. So we had our sad face moment, and now we have our happy face. Okay, and then also notice that it naturally kind of follows our periods of increase and decrease. Increasing on negative infinity to 1, and then 2 to infinity, decreasing between 1 and 2. Okay, and there you go. So we were able to graph this polynomial using only calculus. We didn't really rely on our algebraic methods using end behavior and all that kind of stuff. We didn't have to do that. Or x-intercepts. We didn't really do x-intercepts either. All right, so let's talk about second derivative, and then we'll graph a more complicated function. So we're going to talk about something called the second derivative test. And the second derivative test has the same outcome as the first derivative tests. It tells us about local mins and maxes. Okay, so first of all, if f prime of c is equal to 0, and the double derivative is greater than 0, then f has a local, let's see, if we're greater than 0, it means we're concave upward. So we're a bowl like that, we're happy face. We're facing the sky. So at that point right there, that would be a local min. Okay, and then if we have the same scenario, but the double derivative is negative, right? So we're concave down like that. Well, now that point right there, where the derivative is 0, is a local maximum. And that's the second derivative test. It gives us the same information as the first derivative test, but just in a different way. All right, so when we look at part 3, we're going to be graphing something more complicated using all of our derivatives.